Our first speaker, who also knew Bud Fay's knowledge and humor, is Kirk Johnson, a paleontologist and the director of the National Museum of Natural History. Kirk's full bio, as is the bio of all the speakers, is in your program book. Kirk is going to take us back, far back in time, for some perspective on past changes in the Arctic environment. Kirk?
Did you get mine?
Okay, can we have the podium mics for Kirk?
There's your, okay. Set it away. Awesome. Well, good morning. It's a real honor to be here with you. I've been a paleontologist my whole life, but I have this deep love of the Arctic, and it's just an honor to be in a room with so many people who are from the Arctic and are so knowledgeable about the Arctic. And I want to take you back in time and give you a deep time perspective. And if you have a chance while you're in Washington to come to the National Museum, on June 8th we opened a new exhibit called Deep Time, and it's the history of life on Earth, and it goes into the future. And it has Arctic elements and climate elements that are worth looking at. It's just down Constitution Avenue. So if you have a moment to go see it, some might call it the dinosaur exhibit, but really it's the story of our planet. And the Arctic is such a bellwether of our planet because when the world warms, it warms faster in the Arctic. Now I start this with a picture of a planet's trees because in a way, if you think about our planet, there are places that have forests and places that don't. So look at our trees. We have about 3 trillion trees on the planet right now, which is pretty good. There used to be 6 trillion when humans started chopping them down. They mainly occur in places where it's warm enough and wet enough to grow a tree. Makes some sense. But just look at that. That's our world of trees today. There are about 60,000 different kinds of trees on the planet. It's quite a few. And many of those trees, by genera, have been around for 50 or 60 million years. So in a very interesting way, trees are our planet's memory. Of course, there's ice. And polar ice today seems like a permanent thing because it's so massive and so extensive. If you go to Greenland or Antarctica, you can't imagine how 10 or 12,000 feet of ice accumulated and what it took to get it there. But there it is. So I see the world as a dance between forests and ice. If you go back in time, where forests are located, where ice is located, gives you sort of the fossil evidence of our planet's history. And of course, in order to interpret forests, you need a paleobotanist, and I am that person, so I will guide you on a tour. Now, paleobotanists use very technical research tools called shovels and pickaxes. We're a science that hasn't changed much since the 1800s, and in fact, early explorers to the Arctic found coal seams and fossil plants in the Arctic, which were baffling then as they are now. Fossil plants are pretty amazing things. They're preserved in great detail, and a fossil leaf is like a fossil weather station. You can look at the stomata in the leaves and estimate the amount of CO2 in the atmosphere. You can look at the size of the leaf and estimate the rainfall in the landscape. You can look at the margin of the leaf and actually get a pretty good proxy for the mean annual temperature of where the tree grew. You can also look at the species of tree, understand where those species lived, and you can look at the insect damage in the leaves to understand the ecology of those forests. So a fossil leaf is far more than a fossil leaf. It's a fossil weather station and a map of Earth's past ecologies. When you realize that, it's hard to imagine not being a paleobotanist. And when you're a paleobotanist, you start quickly to realize that rock layers are nothing more than cross-sections of ancient worlds. So when you look at this coal mine in Wyoming, you might see a coal mine in Wyoming. I absolutely see the swamp it came from. And whenever I'm driving around, I'll talk about the ancient landscapes when I see the modern landscapes, and it baffles everybody I'm traveling with. But just the way I think about things. And this started when I was pretty young. I'm from Seattle, Washington, and I grew obsessed with fossils when I was about 5 or 6 years old. When I turned 16, I got a driver's license, which allowed me to explore the American West and do my own fossil expeditions. When I was 17, I discovered a site in northeastern Washington in a town called Republic. Here's the little town. It's a gold mining town in Washington State. That's not me in the picture, but that is my fossil site. On the edge of the road, the side of town, a little town in eastern Washington. The site is pretty interesting because it has a kind of rock called paper shale. The rock splits like pages of a book, and when you pop open those pages, there are exquisite little fossils on the pages of the book. Pretty intoxicating stuff. These fossils were exquisite. Things like fossil flowers popped out of the rock. And I started collecting these things, and within a matter of a year or two, we had over 100 different species of all sorts of different kinds of plants. Flowers, fruits, seeds, pods, leaves, the whole suite of vegetation that lived in this place. And I started corresponding with scientists, and a number of the fossils that were there were from things that were still alive today, from genera still living today. This is a site that's 50 million years old. But those tree genera are still alive today, and they have a modern distribution. So here they were in Washington State 50 million years ago, and I found some curious things like metasequoia. Now, this is called the Don redwood. It was a tree that was discovered in the 40s during World War II in central China. His entire range is in Hubei and Sichuan provinces in China. Curious enough, it's a fossil in Washington State. Or Cercidophyllum, the Japanese scholar tree, which is in Japan and China today. It was in Republic. It became clear to me that the little town in eastern Washington was telling me a story that was a fairly global story. And if you think about it, that Republic site and the modern range maps onto a different pattern that's been baffling botanists for many, many years. It's the fact that broadleaf deciduous forests, the kind that grow here in eastern North America, and in Europe and Western Asia, and in Eastern Asia, all have many of the same genera, but they're widely separated by taiga, deserts, other kinds of ecosystems. These are called the disjunct deciduous forests of the Northern Hemisphere. They've been baffling scientists since they were discovered. And the question is, how in the world can you have three very similar forests that are widely separated? And the answer, of course, is the Arctic. They're all remnants of a once continuous forest that stretched across the Arctic. But the Arctic today has ice and tundra and taiga, not broadleaf deciduous forests. So how did this happen, and how do we know? This is Mary Dawson, an epic Arctic explorer. 1976, Mary Dawson was studying fossil mammals. And not only are there plants that are distributed between Asia and North America, but there are also animals. And Mary had a very simple hypothesis. If you have the same mammals in Paris and in North America, they must have walked between the two places via the Arctic. Let's go to the Arctic and find the fossils of those mammals in the Arctic. She went to Ellesmere Island in 1976, and on her first trip, she found not fossil mammals, but she found crocodiles and turtles at latitude 78. So I learned about Mary's work, and I said, Mary, I must go to the Arctic with you. This is just a non-negotiable thing. Here she was in Ellesmere, and I saw a talk given by Leo Hickey at Yale, who had managed to talk his way into her expedition. And I was so compelled by the concept of my fossils from Washington State, perhaps being in the Arctic, that I inveigled my way onto this trip. And you can see Ellesmere is really north. It's not a very habited place. Grise Fjord's the one indigenous village, and that was a village that was transported to Ellesmere. It's not only far above the Arctic Circle, but it's more than 1,000 miles north of the nearest tree. So it's a place where ice has won the ice-forest battle pretty clearly. In 1984, Mary said yes, and we spent the next 2 summers, Mary and I and 2 more people, on 2-month expeditions to Ellesmere Island, all around the island, looking for fossils on Ellesmere Island. And Ellesmere is an amazing place because it does take you right back to the Pleistocene. These ice sheets lying on the land surface, muskox and polar bears, just huge sheets of ice everywhere. No woody plants except for the prostrate Arctic willow. But if you fly around, there are massively thick coal seams. And if you look at those crumbling white rocks in the coal seams, you find them to be petrified trees. And of course, petrified trees are like potato chips. They don't just get one, you get entire forests of them. And they're preserved well. You can see their growth rings. You can see how fast these trees grew, how long they lived. And they got big. These are not small Arctic trees. These are trees the size of modern redwoods because, in fact, the metasequoia is a close relative of the modern redwood. We found fossils of these trees as far north as Lake Hazen, latitude 84. poles were forested. At this time, there's no evidence for any Arctic ice at all. Similar fossils have been found in Antarctica. So you confront the concept of a world with no polar ice. That's a world that's got forested poles. It is so different from our modern concept of the poles, and it's so hard to explain from a climate model point of view that it remains one of the interesting unsolved questions. How do you warm the Arctic all the way to the poles enough to remove ice, have enough warmth and wetness for forests, and preserve that for long periods of time? Here's the Metasequoia fossils, the same kind that I found at Republic. Here's the Cercidophyllum, Japanese scholar tree fossils, the same kind as I found at Republic. And this one took me a while to realize what it was, but it's in fact lotus. Changes your view of the Arctic to imagine an Arctic with lotus fields and Metasequoia trees. And the fossils were so compelling. Mary would crawl around in the Arctic tundra and pull up the small fossilized jawbones and teeth and skulls of small animals. This is a complete skull. You're looking into its palate. You can see both rows of teeth. It's related to the flying lemurs of Indonesia. And of course, you realize that if it's warm enough for the trees to connect the continents, the animals that live in those forests can also go there. Just 2 years ago, in Homer, Alaska, a 4-year-old child found a fossil tapir jaw. Now, tapirs live in the tropics of America and Indonesia, but there's a Homer tapir now. Here's a flying lemur, Dimopteran, in a Japanese scholar tree in the Arctic. Fossil turtle shells, fossil alligator parts. Here's an alligator for scale. And fossil mammals that come in all sizes and shapes. This is an animal called Coryphodon, first discovered here in the western interior of North America in the 1860s. It's a large hippo-like animal. Here it is at a place called Strathcona Fjord on Ellesmere Island. And there's a reconstruction, early reconstruction of what Ellesmere looked like 50 million years ago with turtles and crocodiles and lotuses and metasequoias and cercidophyllums and platanuses and ginkgos and coryphodons and tapirs. An amazingly different Arctic than we know today. Here's the diorama we built for the American Museum's Natural History's traveling exhibit called Extreme Mammals that shows that same landscape in a three-dimensional form, not the high Arctic that we're used to. And then in 2004, an amazing discovery. A crew drilled a core on the Lomonosov Ridge in the middle of the Arctic Ocean, not far from the North Pole, down to that exposed bit of continental crust, and brought up cores that had the story or the history of the Arctic Ocean. And at the level of the cores that represented about 47 million years ago, they pulled up not marine plankton, but the spores of terrestrial ferns. A floating fern called Azolla. Here's what Azolla looks like. It's a little tiny thing. Each plant's about the size of a penny. They float on the surface of ponds and lakes from the tropics up into the warm temperate region. Here's a picture of what the Arctic Ocean looks like today, and here's a picture of a lake in Amazonia that's covered by the floating fern Azolla. This is your Arctic Ocean of 50 million years ago. A freshwater lens on top of a salty sea covered by floating aquatic ferns. So, that brings us to the story of our planet. The planet really has two major climate phases, and it doesn't switch between them very often. The Icehouse World, which we live in today, where there are polar ice caps that occasionally visit us at mid-latitudes, and the Hothouse World, where there are no polar ice sheets, and where it's warm enough occasionally for subtropical species to invade the polar regions. Now, you're all pretty familiar with the Icehouse Earth. Some of you live in the Arctic. But know that there are two different phases of Icehouse Earth. One where it's cool and one where it's cold. We're presently in a cool phase called an interglacial. During the cold periods, the ice is able to survive at lower latitudes. So here's our present cool phase. If you dial the clock back 18,000 years, you get this. I always love this because you can look at North America and see the Great Lakes of Canada and the United States are merely the footprint of the last ice age. You can see the ice sheet sitting right on top of that. You don't even need to look at a reconstruction. You can see the footprint of the ice age on our continent. I'm amazed how many non-scientists don't even know this basic important fact, that 18,000 years ago, our cities were covered by ice. I'm from Seattle. Here's Seattle 18,000 years ago. A lobe of ice that was 3,000 feet thick in Seattle. And Seattle has a perfectly good little ruler here called the Space Needle. It's 605 feet tall. And there it is relative to how much ice was on Seattle 18,000 years ago. This summer, I had the pleasure of climbing to the tip of the needle of the Space Needle and doing a show I'm working on for NOVA about how much ice covered Seattle 18,000 years ago, which just was not that long ago. So you realize that the world can be colder than it is today and warmer. If you were in Alaska 18,000 years ago, you'd see this amazing megafauna, much of it now extinct, the animals that came into North America from Asia and those that came from North America back to Asia, this great highway. So the transfer of plants and animals from North America to Asia has been going on for well over 100 million years. Starts with dinosaurs, ends up with mammals, and finally people. Probably the best representation of the ebb and flow of the glacial interglacial was captured in this incredible ice core from Antarctica, the Dome Sea ice core, which captured 800,000 years of record, which shows the increase of CO2 and methane in sync with the increase of temperature and their decrease. And you see something in the order of, going back to the present, every 100,000 years or so you see an interglacial. And our present condition is interglacial, but I call your attention to this one disturbing fact, which is over here. This is our CO2 happily marching along with temperature and methane, and our present CO2 is now off the chart at 415. So we're actually in a place we've never been before. For the last 800,000 years, we've never exceeded 300 parts per million in CO2, and since I've been born, when I was born in 1960, CO2 levels were 315. They're now 415. So in my lifespan, we've done something we couldn't do over the last 800,000 years. So don't think for a moment that this moment we're in right now is not unique. This is a unique moment in planetary history. And we happen to be the lucky scientists and people and residents of this planet that are here at this critical moment. Now, you're probably not familiar with the Hothouse World with the no polar ice sheets, and there's no, none of your fault for this. It's in fact my fault and the fault of my colleagues in science who have not taken this amazing discovery and brought it forward more forcefully, because it's such an incredibly insightful thing to think about the world with no ice that we should be sharing it more widely. And I thank you for the opportunity to be here to do that for you here today. Note that like the Icehouse world, there is two phases. In the Hothouse world, you have warm with temperate polar forests and hot with subtropical polar forests. Now, I'm going to use a different kind of plant to demonstrate this. The palm. Many of you have experienced palm trees. I know a lot of Alaskans fly directly to Hawaii when they can, because palm trees grow in warm places. There's about 2,000 species of palm trees in the world today. The first palm evolved about 90 million years ago. So palms are a pretty nice climate indicator. And if you look at where palms come in many different types, 2,000 of them, if you look at where they live today, they live pretty much in the tropics and subtropics. They live both in wet and dry climates. But you notice they can't take any frozen ground at all. That's why they're so strictly knocked off. They're basically, if you go to a place that has any freezing in the winter, your palms are not going to be able to reproduce. So palms are a very nice plant equivalent to a tropical animal. We do find fossil palms in places we don't expect to find them. Here's a fossil palm from Wyoming. If you go to Wyoming, you don't think palm trees. You think it's going to be cold in the winter. So clearly, Wyoming's climate has changed since this 50-million-year-old palm was deposited. I'm from Washington State. Just south of Bellingham, there's a place called the Chuckanut Drive. And if you drive on Chuckanut Drive, on the side of the road, visible from your moving car, are panels of fossil palm leaves. No one's interpreted those things. Again, people are missing one of Earth's most important stories. 2012, I was up in Alaska filming a show called Making North America. And we were on a beach with a film crew I'd taken to Kuperanof Island because I knew there were some fossil leaves in this island. And while we were filming, as the tide was coming in, and much to my incredible pleasure and delight and amazement, on camera, we popped up a slab of rock that had a fossil palm frond on it. Absolutely the luckiest moment in my life. I did not swear. I said something like bingo or something like that. But I didn't know this was there, and to find it on camera was for me that perfect connection of this is a story that must be told at the moment when there was a medium to tell that story. Now that palm frond, the tide came up, we grabbed the adjacent slabs and put it back together. There it is. That's an Alaskan palm, which begged the question, how far north in Alaska did palms get? The next year I went to the Matanuska Valley north of Anchorage, and as you drive the road on the Matanuska Valley, there's outcrops of this rock from the Chickaloon Formation. That stick is what they call an Alaskan climbing stick. It allows you to climb up the side of a cliff when you have no ladder. And the reason we were climbing up that cliff is because that little spot right there is a fossil palm frond in the Matanuska Valley. So there's the palm sites of 50 million years ago. And you realize that Alaska wasn't just warm enough for forests, it was warm enough for palm trees. This is Alaska 50 million years ago. All right, so in the exhibit, we built the first ever science-constrained draft climate curve for the last 500 million years of planet Earth. It's on display at the museum. It appeared in Science in May. This shows 500 million years of time, and you see right away that there are times here in orange where the world does not have polar ice caps, and times in blue when it does. And about 75% of Earth history is times when the Earth did not have polar ice caps. Our present condition is unusual. You can see we've been in that present condition for the last 34 million years or so. So to think about it this way, the last 500 million years of Earth history, 75% of the time was polar forests, 25% of the time were polar ice caps, and our present world from the last 34 million years, our world, the only world we know, the only world most mammal species know, is the less common condition. The disturbing fact is that we might be at a tipping point going back into that Hothouse World. We're not just going to go into a less cold world, we're headed towards a warm world. So this is the same curve I showed you before. This is the one that's on display in the museum. And note that there is a line here, which is the world without ice caps and the world with ice caps. And here we are today. I'm going to zoom in and make this graph more recent in time now. This now shows you now, and notice that we don't put now as the end point because now always goes out of date immediately, right? This is just now, and there's a future. We're interested in the future, and there's a past. This is the last 20,000 years. You can see that humans got to North America, people of the Americas, sometime in this time period. We don't know exactly when. But they got here in a time that it's always been getting warmer. And then at around 10,000 years ago, the climate flattened out. This is the Holocene. This is the time period where all of human civilization occurs. And the last 200 years, now we're started up. The question is, we know we're going up more because there's enough CO2 in the atmosphere that we haven't caught up with it yet. If we mitigate our CO2, we might flatten out at a level like this. If we continue, we could cross this line, the line of the world without polar ice. And that's the point I leave you at, is that we know we're going to a warmer world. We know this is not something that's happened in the past. The last time we left an ice house into a greenhouse was 250 million years ago. This is not a natural cycle. This is a natural cycle plus human activity on top of a natural cycle. And we are at a point where critical global choices are to be made by the 7.8 billion people on the planet. So I leave you with this thought that the world has an amazingly interesting past, and as a person who grew up as a paleontologist and dug fossils because they were fun, I reluctantly agree that they're deeply relevant to our future. And finally, on February 5th, I did a Nova show, 2-hour Nova show about this topic that'll air on February 5th, and I hope you all check that out. It'll be associated with a NSF-funded education program that included expeditions to Antarctica and a whole bunch of web assets. So if you like this talk, there's more to come in February, and thank you so much for your time.